So yeah, let's get straight into the last part, which is we saw at the end of last time that we had that we recovered this page curve, this sign of unitarity from using only semi-classical gravity, but the ingredient that we used to get there ultimately were these replica wormholes, which involved these connections between different boundaries. So to start off with today, I'm going to so probably the first half or a little bit more of today, we'll be talking about space-time wormholes in general and the physics of baby universes that they're associated with. And I'll probably just very briefly outline how this works in a particular example, which is, again, we've seen JT gravity, but the example of pure Joukiev tidal wave gravity. Just give a very brief outline of how this gives a very explicit example that realizes the sort of structure I'll be talking about in the first part. And then with that under our belt, we can go back and give ourselves a new understanding or a new interpretation of these replica wormholes. Unfortunately, that'll leave us in a very puzzling situation, but that's the situation we're sort of in now in the community. So, I hope that some of you listening can help push us forward and help resolve some of the confusion and that I'll talk about at the end. Okay, so the first thing I should tell you is what I mean by a space-time wormhole. So this is the sort of basic idea is that you have some different points in space-time that might be very, very widely separated in time or very widely separated in space. Otherwise, in some maybe ambient, almost flat space. So maybe you've got one point which is Earth today, and then maybe another point is in some distant galaxy many years in the future, or whatever it might be. So a space-time wormhole is then a shortcut between those two things in space-time. So this is a picture on the left. We're always going to be drawing pictures of space-time. So this is, you could maybe think of time running upwards here. And these are the spatial directions. And there's some separation here. So there's some separation in the ambient space, this distance d. And then there's another separation here, which is through the wormhole, some dw, distance through the wormhole. And the basic property of a space-time wormhole is that, roughly speaking, we can take this separation in the ambient space to be as large as we like, and the distance through the wormhole is going to be fixed. So this is a shortcut through space-time. And it'll be useful to make this, to really take this infinite distance limit and think of these as being really two separate spacetimes, so that really in this strict d goes to infinity, distance goes to infinity limit, we just think of these two ends as living in different spacetimes with different asymptotic boundaries. So that'll be a useful abstraction. So a picture of what's going on in space here, you can think of slicing this at different times and see what space looks like. And to begin with, at some early time, it's just flat space. And then you have some process here, which would be some quantum tunneling process usually. And then at some intermediate time, you look at a spatial slice, it contains this, this wormhole mouth. And that wormhole mouth in space looks like this closed universe. So this is a universe without boundaries. So there's some point in the past where a wormhole sort of pops into existence, it propagates for a while, and then it might rejoin space-time at some other point. So this is the rough picture. And the idea is to think of this thing as a so-called baby universe. So you might think of this as being sort of small compared to our parent universe. So this is the parent, and the baby is born from the parent and then reabsorbed later. Okay. Just to contrast this with another type of wormhole, which you may have seen probably more of, these are spatial wormholes. We're not going to be talking about these, but I just want to explain what these are so we don't get confused. Here, the classic example is the Einstein-Rosen bridge of a two-sided black hole. So this is the Penrose diagram of a two-sided ADS black hole, picture of space-time. And if I draw a a spatial slice through this at some particular time, then space looks like this. So the picture of space that we've drawn here looks like the picture of space-time that we've drawn up here. So this is a spatial wormhole and this is a space-time wormhole. So it might be that these two ends are really distant parts of the same universe, like this, or it might be that they're in different universes. And we'll sort of be taking this perspective. Good. So what's the sort of physics interpretation of these for, so maybe we'll think about someone who's far away from these objects and the kind of physics they might see by probing these objects to tell them that there's this kind of connection. These spatial wormholes are something that we're familiar with. These induce correlations in space that can be at arbitrarily large separation. But this is something we're very used to. And in fact, these spatial wormholes provide a geometrization, a geometric version of quantum entanglement. And this is, so this sort of spatial correlation is the sort of EPR correlation, and these spatial Einstein-Rosen bridge is providing a geometric realization of this. So that is this ER equals EPR sort of idea. And this is, this is really just giving us a nice geometric picture of physics we're very happy with. And okay, in the 1920s, it was in 30s, we certainly found this mysterious, but this is something we're very happy with and used to in quantum mechanics. The space-time wormholes, on the other hand, here we have these non-local correlations in space, the kind of things we're used to in quantum mechanics, but here we get non-local correlations in space-time. I'll explain what I mean by that in a moment. But these seem to potentially give rise to physics that's really bad, something we don't want. It seems to break the usual notions of locality we have, or at least it seems to put them in trouble. So a precise version of this is cluster decomposition. This is the idea for example, if you do a scattering experiment, then if you do two scattering experiments that are very widely separated, then as you bring the separation out to infinity, the two experiments become uncorrelated, become independent. This is the idea of cluster decomposition. But a wormhole, a space-time wormhole like this, it looks like a scattering experiment over here and a scattering experiment over here can become correlated and break this. Okay. So that's what a space-time wormhole is. I'll just very briefly give, this is not the main approach I'm going to take today, but want to give one way of thinking about these that works in particular for wormholes that are space-time wormholes that are very small. You might think of them as being sort of Planck-sized or something. And this is something that people thought about a lot in the late 1980s and early 1990s. The idea is to think of this wormhole as being small and integrate it out. So you want to have some effective description for this wormhole where you just say it induces some effect, some correlation between the two mouths of the wormhole. And so you replace the mouths of the wormhole with just local points, these local points X and Y, and you have some operator, you replace it with some operator at Y and some operator at X. But the wormhole then correlates these operators, or these combinations of fields. And so the result is that actually you get an effective action that's bilocal. So the exact operators here and the coefficients will depend on all the details of what this wormhole looks like. But it looks like you're adding this non-local term, a bilocal term to the effective action. This is if your wormhole has two ends. If you had a wormhole with three ends that connects to some other point Z over here, then you might have a three local term, for example. But we'll just give this. And as long as the size of the wormhole is small compared to whatever physics you're interested in, so perhaps we're doing experiments at TeV scale at the LHC, but the wormholes are Planck scale, then we can think of this as being a local effective action with higher derivative terms being suppressed in the usual way in effective field theory. So just to say how this happens, if you have one wormhole, you have an insertion like this in the path integral, or just minus that as a convention. And the way you get an effective action is this gets exponentiated by the fact that you can have n wormholes that connect. So you have one wormhole here and another wormhole, some completely different part of space. You can have contributions from n wormholes up to some symmetry factors, so it gets exponentiated. And this is something that's sort of familiar from Feynman diagrams and so forth. Okay, so this seems bad. Like we said, it breaks cluster decomposition because you started with a theory that has a local action. This is just local sort of Einstein gravity, say. And then you go to a lower scale and you integrate out these wormholes and you get some non-local action. This doesn't decay at all at distances. So importantly, these Cij, Cij is independent of x and y, at least at long distances. So these don't decay with distance. So they seem really bad. But it was realized that they're not as bad as you might think. And the idea is to do this sort of Hubbard-Stratonovich trick that people may have seen, is to write this non-local action or the exponential of this the exponential of the action as a Gaussian integral like this. So now you can see that if you complete the square, so you have some inverse of these coefficients Cij, the details don't really matter. Maybe the easiest way to think about this is just to think of having the identity matrix here and there's just one operator. But you can see that if you complete the square and perform this Gaussian integral over this auxiliary parameter alpha, then you arrive back. This goes something like e to the minus the integral dx, integral dy O of x O of y, with some coefficients. So if you perform this integral, you get back to what we started. But now, this piece looks like a local effective action now, where we don't have a bilocal term anymore. There's only one term. But here we have these alpha. So this alpha is like a coupling constant. So one thing you could imagine, for example, is that through these wormholes, a particle can go in and come out again. And if a particle goes in and comes out, then this operator might correspond to, say, the field squared, say. That's probably if two particles go through. But so if this operator corresponds to the field squared, then this parameter alpha is something that's shifting the mass of the field. So it looks like we've got this coupling constant alpha, or a shift in the coupling constants of our theory, except that it comes with a weighting. So one way to describe this is that this is a probability distribution. For the couplings of the theory. So we have a local effective action at the expense of introducing this random parameter. And alpha here is something that's completely independent of space-time. It's uniform across the entire universe. It doesn't vary here to there. It really behaves like just a parameter of the theory. That once you fixed it, it's constant for all time. Okay, and this is really the main physics that we're going to see in a different way, in a slightly different framework. But this idea that the space-time wormholes, they do lead to these spatial correlations, but what they lead to is this sort of classical randomness or classical probability distributions. And one way to understand these classical probability distributions is that they refer to the state of these baby universes, and because you can't observe the state of baby universes, you get this uncertainty. We'll talk about that in more detail. So this is still potentially important, and people talk about this a lot. So for example, this is an idea of how you generate potentials for axion fields. So there's a famous class of wormholes, the Giddings-Strominger solution, that are these wormholes that are supported by axion fields, and these things would potentially generate potentials. So there's some interesting physics that sort of particle physics that you could potentially get from this. We won't be talking much about that in the rest of today, but this review is very nice and talks about these ideas in a lot more detail. So I'd recommend that if you're interested in that. Okay. So we're going to take a different approach, but I'll pause to, don't worry too much about the details of this, because we'll be taking a different approach. But if people have burning questions now, then speak up. Okay. So I'm going to take a
Henry.
There's a question in the chat.
Sorry, I just have a question. In what sense we can think of these wormhole actions to be non-local?
Yeah, so it's non-local. It's non-local in the sense that the correlations it induces are completely independent of the separation of the wormhole mouths. So it's not. So it's not like you get correlations that don't decay with distance. So for example, if I introduced a new particle into the theory, some new interaction, that induces correlations between different points in space-time, but they decay with distance. So if I integrate out this particle, then it gives you an effective action that's local on the scale of the mass of the particle. So you don't get something like this. Or again, so I mean, strictly speaking, you might get something bilocal, because where the coefficients are given by sort of the propagator of the intermediate field. But here, because these wormholes can connect arbitrarily distant points with the same amplitude, that's why it's non-local. So the correlations don't.
Thanks.
The same amplitude, that so presumably is a consequence of the fact that so somehow the gravitational action does not decay as, you know.
Yeah, it's because of the fact that we're really summing over geometries, and it's maybe a better way to draw these pictures is which you sometimes see where you have space-time that's sort of folded over, where you have a wormhole connecting the two branches of the fold, because that makes it clear that I can move it. The distance here can be as long as I like, but the distance here can be as short as I like. And that's just the nature of gravity, the fact that we're summing over geometries. We're not working at a fixed geometry, but we're summing over geometries, and you can always add a handle that's as short as you like to connect 2 points.
I see, thanks.
Okay. Good. So so the approach we're going to take now is going to be a bit more abstract or axiomatic, which I hope is not too abstract, and we'll get to some concrete examples later. The great power of this is it means you can make some fairly weak set of assumptions that you're very specific about, and say some quite general things that are going to be very robust and not. This depends a little bit on details, but this approach is going to be a bit more robust and doesn't have sort of corrections and so forth. So the main idea is to think of a gravitational theory in some abstract way as a thing that takes a set of boundary conditions and it gives you amplitude to those boundary conditions. So you have some set B, which is the set of boundary conditions you allow, and for each set of boundary conditions, it gives you a number. So the idea here is that your boundary condition is maybe some manifold that lives off at infinity, and so maybe it's giving you some asymptotic values of fields, which is, so it tells you what the metric looks like asymptotically, and it tells you what maybe some matter field look like asymptotically. And then to get this number from the boundary conditions, you compute the path integral with those boundary conditions. So I've written it in Euclidean here, signature here. It could be Lorentzian as well. But if you want to be concrete, let's think about Euclidean amplitudes, but bear in mind that it could be, that it need not be Euclidean. Okay, so again, this is quite general, and you could have a version of this that works in asymptotically flat space or works in cosmological settings, depending on the exact physics and the sort of boundary conditions you impose. But to be concrete, a nice example to have in mind is the ADS-CFT correspondence, and we'll sort of stay in that context with our notation and so forth today. So here you have some manifold on which you have some say d-dimensional manifold. D-dimensional manifold. Actually, I've written that here. So the boundary manifold is d-dimensional, and you're doing a path integral over d+1 dimensional spacetimes. And when you do this path integral, the number you arrive at, it's by the duality, is supposed to be the partition function of some dual CFT on this manifold M. And the boundary conditions for fields other than the metric tell you about sources you can insert. So this partition function is something extremely general. It includes things like correlation functions, which correspond to having infinitesimal sources for some operators. So this is really the most general thing that you could ever compute in this boundary conformal field theory. Is supposed to be given by a path integral with the appropriate boundary conditions. Okay, something that sort of abstractly you can do that the more mathematically inclined might like, but you can sort of ignore this if you don't, is that you can think of the space of boundary conditions as an algebra. Is you're allowed to take superpositions of different boundary conditions. That's just a very formal thing, is you say, you just define different boundary conditions as 4 of boundary condition 1 plus 7 of boundary condition 2, and then this path integral is defined to be linear. So that's just a formal thing. And there's also a product of these things, which is commutative and associative. Commutative and associative. So it's an associative algebra where the product of boundary conditions is given by just disjoint union. Is you have two manifolds that could be your boundaries, and you just do the path integral with the boundary condition consisting of both of those manifolds. And there's an identity in this product, which is that your boundary is empty. Of course, the disjoint union of an empty manifold and any manifold is manifold. We won't use this in great detail, but it's for the mathematically inclined, this is a nice structure. So let's just be a little bit concrete. Think about some two-dimensional theory of, say, dilaton gravity, like JT gravity we talked about before. Then the boundaries, we had some boundary condition before where the dilaton behaved like, I think it was at gamma over epsilon, and the metric ds squared. So maybe we're in Euclidean space now, dt Euclidean squared over epsilon squared. And we take epsilon to 0. So these were our sort of boundary conditions. And so really the only physical thing left here is to tell me what the length of the boundary is in this renormalized time. So the only one-dimensional manifolds, closed manifolds, say without boundary, are circles. And you could include intervals, but let's stick with circles. And beta here is the length in this Euclidean time coordinate. And the space of all possible boundary conditions is that you just give me n circles. So my manifold consists of n different circles with different lengths. And then when I do the path integral, I sum over geometries that maybe these two are connected and they've got some topology, and maybe this guy is on his own. You sum over all the, and maybe there's some closed universe over here, some closed spacetime. You sum over all the geometries like this to compute the partition function. So this sum z of m or it's a function of just these n lengths. So again, if you want to have a concrete idea in mind, the path integral is computing, this z, this amplitude is computing the path integral for gravity with n circular boundaries. Okay, so that's the sort of framework we're going to live in. And let's just say straight away that there's a potential problem with that, with space-time wormholes. So this here is a space-time wormhole. So for us, we're going to define a space-time wormhole as any geometry that connects two boundaries that were otherwise disconnected, two or more boundaries. So anything that provides connections between otherwise disconnected boundaries. So if I compute this amplitude, this gravitational path integral, where I've got two boundaries, M1 and M2, I can of course have geometries that are completely separate, but I could also have geometries that connect the two. Whereas if I just compute the product of amplitudes, maybe you could think of this piece as being a path integral over red spacetimes, and this piece is a path integral over black spacetimes, and they can never connect each other. They're always separate. So it doesn't include terms like this. It doesn't include space-time wormholes. So it seems that they could be different. You could get different answers. There's also just a slightly sort of subtle point is that if you're including closed spacetimes, then there's a slightly different way they appear in. That's less important. But the basic idea is that if we had for a gravitational theory to begin with, this isn't necessarily a problem. But the ADS-CFT correspondence tells us something remarkable. The non-trivial part of the ADS-CFT correspondence is that this theory is local on M. So it has some formulation in terms of a local action on M. And one very weak consequence of being a local theory is that this should be equal to this. So if you do the path integral on a disconnected manifold, it's the same as doing it separately on each manifold. So that's why it's called a problem. At least in the context of ADS-CFT, this is potentially a problem. Good. Questions? I want to make sure that people have this, the idea of this sort of abstract definition of a theory of gravity clear, because it's we're going to go to Hilbert spaces now, where it gets I'm afraid the abstraction is going to get briefly worse before we start bringing it back to something concrete.
Henry, I have a question.
Yes.
It looks formally like this it looks like 2D string theory, for example. You fix the boundary conditions and then you sum over all world sheets. So is that analogy just heuristic, or is there, I mean, how precise is that analogy? Can I think of this AB universe as just doing string theory?
Yeah, so that is a really interesting question. At this level, you can certainly think of string theory in this way. So in that case, your manifold, because in that case, you can think of your boundary manifolds as being a set of vertex operators, for example. And there, it's definitely not a problem that you have this factorization. That's strings scatter. So it is. So that's fine. So yeah, there are some subtleties in exactly how you think about string theory as a theory of quantum gravity in 2 dimensions from the point of view of the world sheet. Actually, there's a paper that should appear later this week or next week that explores that a little bit more for world-line quantum field theory, but I perhaps don't want to get into that now. But
okay, thank you.
It's an interesting question to dig into a little bit more, but I think not for today.
Okay.
Henry, I have a question. So in case of flat space-time, the boundary condition M is defined at no infinity?
Yeah, so yeah, think of M as being, so it wouldn't be, so in this case, with ADS-CFT, we can really think of it as a manifold. perhaps up to some up to some conformal class. Here in the asymptotically flat space case, we should think of M as being maybe telling us something about how the fields are falling off at scri plus and scri minus. So, or a very nice way to think about a possible set of boundary conditions is as a set of in states and out states of the S matrix. So the usual data that you put into a scattering experiment. And the only difference in gravity compared to the usual S matrix in quantum field theory is that we include a downward metric in the bulk. But in terms of the data at infinity, the scattering data, so you have effectively a free Fock space, and so you can define different particles with different momenta and polarizations, and that defines your boundary conditions in that case. And then Z is an S matrix essentially.
Okay, thanks.
So thanks for that question. And there's something similar in cosmology where you might think of this Z of M as being computing correlation functions in the CMB, something like that. Okay, let's talk about Hilbert spaces then. So just to warm up, in quantum gravity, this is something that's unfamiliar and is going to look strange, but it's going to be almost identical to a particular way of talking about quantum field theory, where it's a little bit more, it might seem a little bit more familiar, but it's almost, what we're going to arrive at is almost identical to what we're a little bit more used to in quantum field theory. So a Hilbert space in quantum field theory is associated to spatial manifolds. So the idea is that you have some amplitude, so you compute a partition function on some manifold, maybe with some operators inserted, so operators here and so forth. And a Hilbert space interpretation is what you get when you sort of cut the path integral. So you cut it in two, there's some spatial manifold sigma, and then you think about this as being a sum over intermediate states that live on sigma. So this is where you get Hilbert space from. This is sort of exactly the same as, this when we're computing entanglements and so forth. This cutting and gluing of path integrals is really we're really thinking about these cuts as being where Hilbert spaces live, sums over intermediate states. So in our case, these manifolds sigma are d-1 dimensional. So in this case of 2D gravity, d equals 1. So these are points, because our quantum field theory is just a quantum mechanics, or sets of points. And then we define states by saying, we've cut this in two, and we're thinking about this as an overlap of different states. There's a state that's coming in, maybe psi, call it psi minus, and then there's the bra state psi plus that's associated with the top. So this amplitude, Z of M, if you like, is going to be computing the overlap between these two states. So if you just have half of this manifold, call it M minus, it's a manifold with boundary, that's what we mean by state, or there's a state associated with that. So you have some manifold with boundary, and that boundary is sigma. And that gives us a state in the Hilbert space, H sigma. So let's just take an example where our sigma is a set of two spheres. So, one state we can make is a manifold with boundary, where the boundary is two spheres, is you take two hemispheres. So these are d-dimensional hemispheres. So if we take this to be our manifold, then we'll get some state. So in CFT, this is the way you construct the vacuum state. This is equivalent to some infinite cylinder, conformally equivalent to infinite cylinder in CFT. But in any case, we get a product of two states. In the conformal field theory, this is the product of the vacuum state. Another manifold we could use that has the same boundary is this sphere, this spatial sphere times an interval of some length. And this defines the thermofield double state for us. So this is just some examples. Maybe I should say this way of thinking about quantum field theory is very, very common in topological quantum field theory. So especially if you look at the TQFT literature, this is really the way people talk about sort of axiomatized, like a Tier's axiom for topological quantum field theory come from exactly this kind of idea. Okay, so now we're going back to this picture at the top. We want to compute these inner products. So the inner product is given just by what we said before. You take the manifold M minus associated with the Ket state and the manifold M plus associated with the Bra state, and you glue them together. The only slight subtlety that we won't spend too much time talking about is that you need to have some antilinear map, some notion of reflection. So you think of this as CPT conjugation, but that we won't worry about that too much. I'll try to have the daggers in the right place, but you can sort of ignore the daggers and you won't go too far wrong, at least for the ideas. So an example here is that if we take two overlaps of these thermofield double states defined by these cylinders, then the definition of the inner product is you take these two cylinders and you glue them together along their boundaries. And when you take two cylinders and glue them together along their boundaries, you get a torus. So this is really the thermal partition function at some temperature on this sphere, as you expect from the thermofield double. Fine. And we always expect that when we construct a Hilbert space like this, that it's really a Hilbert space, that all our states have positive norm. So any state psi has to be bigger than or equal to 0. So this actually is really a definition of this Hilbert space. Is I give you a set of these states defined by sort of half of a manifold, if you like, some piece of a manifold that has the boundary sigma. I've defined the inner product, and if I have a set of states and the definition of the inner product, then that's enough to give me a Hilbert space. The only technical issue here is that you really need a Hilbert space should be complete, so you need to take some completion. So this is one example of this is the Osterwalder-Schrader construction of Hilbert space in quantum field theory, which people may be familiar with, where in that case your manifold, this M minus, is just a half space, is always a half space, except you can insert some operators, possibly smeared operators. And then these amplitudes are given by the correlation functions of these operators, and you can construct the Hilbert space like this. So if you're familiar with that, that might be useful, but don't worry about it if you're not. Okay, so that's quantum field theory and a sort of a very abstract way of thinking about Hilbert spaces. So any questions before we go to gravity?
So in this case, we don't have any ensemble issue, right?
So I haven't mentioned ensembles. You can ask me about that later, but yeah, we'll see where they come from in a bit.
Okay.
Yeah, so actually I haven't told you the full set of axioms. Locality here would include this idea that the partition functions factorize for disjoint unions. Actually, yeah, let's just going to gravity is actually not that hard. All you do, you have exactly the same structure. Nothing changes except the words. Is now, instead of M minus being a sort of partial manifold where our quantum field theory lives on, this is a partial manifold defining boundary conditions. So it's a boundary condition up to some surface sigma, and to make a complete boundary condition, you have to glue it to something else. So we have our, so it's really precisely the same. And then our inner product is, again, you take two possible boundary conditions with the same spatial manifold. To take the inner product, you glue them together, and then you compute the gravitational amplitude now with that full boundary condition. That's the idea. so this has given us a really a kind of abstract structure of quantum field theory, which is that first of all, you have to tell me what your set of boundary conditions are. Then you have to tell me how to compute amplitudes for your boundary conditions. And so that gives you amplitudes, but we want to go a little bit further and get a Hilbert space interpretation. So we can use the usual language of quantum mechanics and really think about this as a quantum theory. So to do that, we need to, first of all, choose this CPT operation, this dagger operation. This really is, this really is a separate choice, but don't worry about it too much. And that's then enough to define a Hilbert space in this a Hilbert space for every sigma in this kind of abstract language. And then we really want this to give us a sensible Hilbert space. So we're talking about quantum mechanics. And the key extra ingredient that we need is that we get a positive inner product, that we don't get negative norm states. So we're really going to take this as our definition of a theory of quantum gravity. A set of boundary conditions, a set of amplitudes, and this conjugation map that together give us Hilbert spaces with positive inner product. That is going to be what I mean by a theory of quantum gravity. So this I can think of as like a consistency condition, that this is quantum gravity and not it really is a sensible quantum theory. Good.
Henry, I have a question actually before you go on. I'm a bit confused why you said this is the same as in regular QFT, because in the ATIA axioms, you would assign a Hilbert space just to a single circle, right? You would.
Yeah. Okay. So the slightly
You're not doing that.
Here is that I haven't given you a complete set of axioms. In quantum field theory, say in TQFT, you have a locality axiom, which means you only need to assign a Hilbert space to connected manifolds, because disconnected manifolds is just going to be a product of Hilbert spaces. And that's the assumption of factorization, essentially. Whereas in gravity, there's no obvious a priori reason why you expect things to be local. This is why ADS-CFT is magic. It's the magic of ADS-CFT is this locality. So it's the fact that quantum field theories have extra natural axioms. So the only difference is that I'm going to drop that axiom. But thanks for pointing it out, so I can make it explicit that I'm assuming a little bit less.
Okay.
Hi, Henry. Why I'm a bit puzzled about the ETEM2 define amplitude. How do we know that amplitude in gravity is for sure a necessary or well-defined thing?
Yeah. So I think this is basically the set of predictions for the theory. I think if you don't have amplitudes, then you don't have a theory. It may be best to think about the asymptotically flat version. This is saying that there is, at least in principle, some way to compute an S matrix. And I think that's a reasonable minimal requirement for a theory. But perhaps you might just say that that you don't get amplitudes for sort of all possible boundary conditions, but that's fine, because you can just restrict to the boundary conditions. All you have to do is restrict this set to the space of boundary conditions where you can compute. But, yeah, I don't really know what a theory means if you can't compute amplitudes. Perhaps you had something else in mind. So ask again.
Oh, just from like naive, like perturbative gravity, we know amplitude will have lots of problems. And just...
Yeah. Okay. No, I see. Yeah. So often we've only really defined our gravitational theory in some semi-classical limit, or we only know what it is in effective theory. So we don't have a complete definition of the amplitudes, but only in some perturbative sense. And even then, in effective field theory, we don't necessarily know exactly what we're doing. It's not necessarily completely systematic. And yeah, that's a sort of potential problem. And there's a question as to how much of this structure remains intact once you only have that sort of approximate notion of amplitudes, or asymptotic, some asymptotic series, for example. How much of this structure remains intact? That's a great question, but for today, I'm going to assume that I'm really good at quantum gravity, and I've got some complete definition of a theory where I really can compute things exactly. But,
Okay, thank you.
That's hopefully I'll get the chance to make some comments at the end about sort of speculations, and that will be a very close response.
Hi, Henry. So in the case of ADS-CFT, when you have, say, multiple boundaries, so normally, I mean, one way of thinking about them, it seems would be you would have to specify how the state of the quantum field theory may have to be, you have to consider that, the state may not factorize. Right? So,
yeah, well, we haven't actually sort of got to the factorization piece yet. So, yeah.
It could be some sort of more complicated version of the EPR kind of,
So yeah, so I want to make two sorts of factorization distinct. One of which is, and it's related again to this distinction. There's sort of EPR failure of factorization, of the fact that you can have states that don't factorize. That's fine in quantum field theory. And in fact, this is an example. The Hilbert space factorizes and the amplitudes factorize, but it doesn't necessarily mean that all the states factorize. Not every state has to be a product state, and that's just quantum entanglement. So that's never a problem, even in quantum field theory. Okay, one sort of what might seem a technical point that I just want to briefly make is that when we construct this Hilbert space, because this set of boundaries is but we wouldn't necessarily expect to have to get a complete Hilbert space just by just using the strict boundary conditions. Roughly speaking, we need to be able to take infinite linear combinations of different boundary conditions to get to every state in the Hilbert space. And mathematically, to do that, you need to have a completion of the inner product. So there's a mathematical procedure of where you do that. Starting with a positive semi-definite inner product, you construct a completion. But one of the features of that completion is that you can have null states. And that's, roughly speaking, there's some linear combination of boundary conditions that look different that can turn out to be exactly zero and have zero norm. So it seems like a very technical thing, but these turn out to be rife. There's lots of them in examples of gravity that we know. They turn out to be lots of these. I'm not really going to use that later, so I won't belabor that too much now. Just worth pointing out. Okay, so now we're going to talk about one specific Hilbert space that we're going to elevate above all the others, and that's when our spatial manifold is completely empty. And so we're going to call the Hilbert space associated with the empty spatial manifold, boundary spatial manifold. We'll call that the Hilbert space of baby universes. So the reason here is that now states in this Hilbert space, states M, are going to be associated to closed manifolds, M. So the boundary conditions are going to be closed manifolds. And that means that, so we're creating some initial state with a boundary condition, M1. And we have some final state with a boundary condition, M2. And then we're computing the gravitational path integral that includes all these geometries that connect them. And now we can think of our Hilbert space interpretation as the intermediate states as we're cutting this. And the thing that's running between them now are these closed universes. So universes without boundary. So roughly speaking, sigma tells us about the spatial boundary of our universe. And empty sigma means that our universe doesn't have a spatial boundary. That is to say, it's a closed universe. And in analogy with these, it's very closely analogous to the pictures we had before. So we're going to call this the Hilbert space of baby universes. Yeah. So you can think of there's some parent universe attached to a manifold M1, and it happens to produce the baby universe that propagates to another parent. Okay, and now if we take the inner product of two states, then it's computed by the partition function, or the gravitational path integral, say, with a disjoint union. So we're gluing together M1 and M2 along their boundary sigma, but sigma is empty. So they're just separate. So we're just taking a disjoint union. And as we pointed out in quantum field theory, there's this locality. So that means that this inner product is a disjoint union, and the disjoint union just factorizes as a product of the two pieces. And if an inner product factorizes like this, you can think of this, it's like a row vector times a column vector or something. It's it means that this inner product is rank 1. It means that the Hilbert space of baby universes has only had one state up to scaling. So it's basically Z of M1 tells you how much of that state you have. That you get a one-dimensional Hilbert space. So this HBU is very boring, but the whole point of what we're going to be doing now is talking about gravity, where if you have space-time wormholes, you have this failure of factorization, then you can end up with a non-trivial Hilbert space of baby universes that's more than one dimension. So this is the key point I want to make, is that factorization is associated with having a one-dimensional Hilbert space of closed universes. So from a gravitational point of view, this was very special and very surprising, because it tells you, roughly speaking, that there's no physics of closed, or there's the set of, you might think that you can make different states of closed universes, but you can't. They're all the same. Okay, so there's one way to talk about this construction of the baby universe Hilbert space that we've been talking about. Okay, so a way to think about this is that associated with each of these closed manifolds, so these manifolds live in these set of boundary conditions, there's a way to think about a manifold as being an operator on the baby universe Hilbert space. And what that operator does is it just adds this manifold into the state. This is just an abstract sort of definition. So you can think of this as being, you define some state with a manifold M2, and this defines some state. And then you throw in another manifold, M1, which is allowed to join in with your universe and interact. So you have the state. You can think of sort of inserting a complete set of states here, and you get the state M2. And you can think of inserting a complete set of states here, and you have the state M1 union M2. So you can think of this piece of the path integral as computing an operator. And this operator is very special, or these set of operators are very special, is the fact that disjoint union commutes, that it doesn't matter if you, which order you do it in, it means that these operators commute. I should also mention that it is well defined when you do this completion, but it's a technical point. Finally, the adjoint operator is by our definition in our product. Okay, again, these are sort of technical points, so don't worry too much about this. The main thing is that it's commutable. So we have these set of operators, and we also have a special state, the no boundary state. So you might sometimes called the Hartle-Hawking state in the cosmological context, but this term is a little bit overloaded, so I'm going to try to call it a no boundary state. And this is the state where our original boundary, there's no boundary. So that means that down here there's no boundary, and our universe is closed. So just abstractly then, these states, so this state is equal to M1 disjoint union, M2 disjoint union, up to Mn. This is the same sort of state we had before. This gives you the whole Hilbert space, essentially. So you can start with the no boundary state and act with these operators, and you get to the whole Hilbert space. And the gravitational amplitude you can think of as a matrix element of these operators between no boundary states. Again, if you go and chase back through our definitions, then you can check what this is. So all of these facts together can be summarized as the fact that these operators form a complete set of commuting observables. So, it's like when you do quantum mechanics, you have a Hamiltonian and maybe some angular momentum operators, and then these, so maybe you have in the hydrogen atom, you have a Hamiltonian, you have J squared, and you have J3. And these form a complete set of commuting operators, and that means you can label states by their eigenvalues of angular momentum, L and M, and energy, E. So you end up with, the states labeled by N, L, and M. We can do the same here. We can diagonalize them. And what does it mean to diagonalize them? Is you look for the sort of the simultaneous eigenstates, the psi LMNs. But in this case, we're going to label them with a parameter we're going to call alpha. And it is not an accident that we called these parameters alpha earlier. They're the same thing. Good. So the fact that they're eigenstates tells us that the operator M acting on alpha is given by some complex number, which we'll call Z alpha of M, and these are the eigenvalues. Okay. I hope this isn't too fast. But now the upshot is that we can go back to our amplitudes. So the most general amplitude we can write as an amplitude with this disjoint union of boundary conditions. We can write it as this matrix element of these operators that insert boundaries. So you start without any boundaries, you throw in these n boundaries, and then you compute the path integral. That's what this inner product means. And now we can just insert a complete set of states. So this is just a resolution of the identity. Sum over alpha, alpha, alpha is equal to the identity. That's what it means to have a complete set of eigenstates, a complete set of commuting observables. So now, because these alphas are eigenstates for all these operators, these just, when you hit alpha, you just pull out their eigenvalues. So you just get the eigenvalues, and all you're left over with is the inner product between the alpha states and this no boundary state. So you end up with a weighting which is given by this matrix. And because we've assumed that we have a sensible quantum mechanics, this thing is of course bigger than or equal to 0. So this is we're using this fact that our inner product is positive definite when we do that. Okay. So our amplitude that we started with, we suggested that in the presence of space-time wormholes, it wasn't obvious that it should factorize. That this should fall into pieces. But if we throw away this sum, then it does factorize. The only way it fails to factorize is by having a superposition of terms like this. So that means that one way to think about this is that we have a correlation between what's going on in these different boundaries. And to begin with, we have this whole Hilbert space structure. So you might think they can have sort of quantum entanglement. But this is telling us that you can't have quantum entanglement, you have this very special sort of correlation, which is classical correlation. So this is saying that, if you like, this is a moment of a probability distribution, and these are random variables. So in our ADS-CFT context, this suggests a generalization of ADS-CFT. So we do this gravitational path integral with n boundaries, and we have this result, which is what we just derived. And we think of the alpha as being a label for not just a single dual CFT for a theory, but some set of many possible dual CFTs. And then the Z alpha of M is the partition function for that CFT labeled by the parameter alpha. So this is sort of ensemble duality, where you have not just a single CFT, so you have a single gravitational theory, but the amplitudes give you a weighted average of amplitudes in in a set of many dual quantum field theories. And then, okay, we just talked about the no boundary Hilbert space. I'll just very quickly mention that if you have the more general Hilbert spaces with boundary, then you get this sort of direct sum structure. The Hilbert space splits up as different blocks. So there's a different Hilbert space. So states can basically live in different sectors alpha, and the operators, these operators that correspond to the boundary conditions, are always block diagonal. So they never mix different alphas. They act within a given superselection sector. This is actually, yeah, okay, I won't mention that. Okay, so this is a little abstract. I'll just very briefly outline one example. I'm not going to explain the details because I want to get onto the last part, talking about Hawking radiation. But
can I ask a question? So you're talking about von Neumann algebra here?
I'm not really talking about von Neumann algebras because, or at least I don't need the full power and technology of von Neumann algebras. So you can say this is the GNS construction and so forth, if you think about that, but I haven't really, because we just have this commutative algebra, I don't really need the full structure of that. So that really needs things like extra data. You need things like operator norms and that we never made use of. So you can use that language if you like, but it's more sophisticated than you need.
Okay, thanks.
Yeah, so maybe if you were, if you were talking about these Hilbert spaces and you were being careful, then perhaps you need to. No, I think it's fine as long as sigma is a closed. I don't think you ever have to worry about von Neumann algebras. They're always type. Well, I can't remember which type. They're never the sophisticated types of von Neumann algebras. Okay. So the example we're going to talk about is pure JT gravity, and I won't go through all the details. And so what I'm going to tell you is very nicely explained in a paper by Sadchenko and Stanford, JT gravity as a matrix integral, and that paper is very clearly written. And if you want to go through all the details, then this is the must-read paper. This is the most important paper to read in the last few years, perhaps. So, but I'll just give you the punchline. So remember that we had this JT action. We first of all had this Einstein-Hilbert piece, and that was topological. It was given by an Euler characteristic, telling about the topology of spacetime. And then when you went on shell, we ended up with just this boundary action, this Schwarzschild piece. And then the path integral was over manifolds with constant negative curvature. So the first thing you can do is to define the amplitude So this really is, I'm going to talk about the connected amplitude where you have n boundaries and we just have space-time that connect the boundaries. So you can, of course, construct more general amplitude by having many of these. But this, because of the topological piece, you can write it as a sum over topologies. And in two dimensions, topologies are easy to classify. It's done by Euclid, I think. Yeah, done a long time ago. And they're classified by their genus. And so you end up with this expansion in terms of S0, which we'll think of as a large parameter. And then you get an amplitude for a given topology. And to compute the amplitude of a fixed topology, we have a surface of constant negative curvature that has some number of boundaries. And you can always cut a surface of constant curvature at some geodesic that's homotopic to the boundary. So you sort of start at the boundary and you take some curve there and you shrink it and shrink it and shrink it until it's a geodesic, until it's the shortest path. So what we do is we cut our manifold until it has geodesic boundaries, and then we split the path integral into two pieces. There's one piece that comes from the outside of the boundary, these are trumpets, and there's one piece that comes from the inside. So the outside pieces, this is essentially this Schwarzian piece, and it's defined by both the boundary length and the length of this geodesic, where we cut the manifold. And then you have to integrate over all possible manifolds in here, and this gives you the so-called Weil-Petersen volume of hyperbolic surfaces, which is just integrating over all possible manifolds with an appropriate measure that comes from the JT path integral when you're. So you have to be careful and read the paper, but that's what you arrive at. And cutting a long story short, there's you can determine all of these volumes and then determine all of these partition functions. And the answer you get, order by order in this expansion over topologies, matches exactly what you get by a matrix integral. And the next thing is to tell you what a matrix integral is. So the answer you get matches with if you computed this instead. So these are our gravitational amplitudes defined by the path integral with n boundaries. And these are computed just by integrating over some n by n matrix with a particular very special sort of measure. And then for each boundary, you insert one of these traces of this n by n matrix, a partition function. And so this is this version of ensemble duality. So here we have a duality between 2D JT gravity and some one-dimensional quantum mechanics. And we have just this, the only structure of this quantum mechanics is the Hamiltonian. It's the only operator that we have access to. And so this is really the most general thing you can compute in this dual quantum mechanics, except that the Hamiltonian is random. You have to integrate over all possible Hamiltonians. So strictly speaking, there's some limit you have to take where these matrices become large, and you tune that limit so that you get back what you expect. But once so this fixes what the potential is, if you like, is just by looking at the disk. So this is, you'll recognize this calculation from when we computed the Bekenstein-Hawking entropy. So this piece here is essentially what we computed before, is the entropy is the value of the dilaton at the horizon, comes from this exponential, and this is a one-loop correction. But okay, don't worry too much. I want to get onto it. But another way to write this integral over Hamiltonians is to diagonalize them and write it as an integral over their eigenvalues. So as an integral over energies. And this piece here is a Jacobian from the change of variables. It's a so-called Vandalman Determinant. Don't worry about it too much, but yeah, it's what you get from changing variables from the Hamiltonian to the energy eigenvalues. But the way to interpret this now is that we should think of this integral here as being this sum over alpha we had before. So this is like the sum over alpha. We then have this piece here. So let's just say this piece here is giving us the sum over alpha. This piece, this is the weighting P of alpha. It's the probability of having some particular set of eigenvalues. So our super selection sectors, our alpha states, are labeled by all the energies of the theory. The probability or probability density of getting some particular energy is given by this weighting. And then finally, you have these Z alpha of betas. So we'll this is the formula we had last time, the sum over alpha, a weighting P of alpha, and then a product of these partition functions labeled by alpha. And we have precisely that structure here. Where now these partition functions are given by the partition function of this Hamiltonian with these eigenvalues. The extra piece that we get by thinking about these baby universes is that we think of this integral over energies, this piece here, we think of this as a sum over intermediate states of baby universes. So the fact that these different boundaries have these correlations, that you have this sum over energies, and you don't get this factorization, is because there are correlations mediated by exchange of baby universes. Good. This is about the. Sorry if it's perhaps a little bit rushed. I wanted to hurry through this to get to the stuff about radiation. Okay, so JT gravity gives us quite an explicit example, and there's you can dig into the structure a bit more, but that's plenty for now. Okay, so let's talk about replica wormholes and try to interpret it through this lens. So the first thing to say is that we had a picture a little bit like this last time, where we were when we were computing, when we were talking about this sort of replica trick, computing the entropy of radiation. We had this reservoir, and we had an interval where we were catching some radiation. We wanted to learn something about the state of radiation, and then that was coupled through this gravitational region. And the rule we assigned at that point was that we were going to fix everything going on over here in the reservoir, but then we'll sum over all the possibilities in our gravity region. And you'll notice that that's exactly the sort of rules that we've been using today. Is we're fixing something on the boundary, and then we're summing over everything that's allowed in the bulk, in the gravitational piece. So in other words, this calculation, rho ij, that fixes the fields above and below the cut in some particular field configuration, these give us components of the density matrix, rho ij's. And from the gravitational point of view, we can think of these as a boundary condition. So this looks a little strange because you have there's a whole quantum field theory going on over here. You're doing a whole path integral, but you can always think of this as a boundary condition here, where you think of the weighting of any particular boundary condition is evaluated by computing this whole path integral in the reservoir. So it's just a complicated version of what we already had. It's just a boundary condition for gravity. So now there's a couple of different things we can do. And I want to contrast two different possible calculations we can do. So one thing we can do is to compute, is to just start with a single replica like this, and either compute the components of the density matrix, or perhaps what we want to do is insert some operators here, and we compute the expectation value of these operators by then summing over I equals j. So that's that's one sort of calculation we can do that's to ask us things, to tell us directly about the state of radiation. So this is how, say, we discussed computing stress tensor expectation values when we computed when we were looking at Hawking radiation right at the beginning. We computed with a single replica. So doing the calculation with just one boundary, we can write it in this new language as being a correlation function of this boundary inserting operator between no boundary states. And using our wisdom from last time, from what we just learned, we can write this as a sum over different alpha sectors with our weighting with some eigenvalues, which I call rho ij superscript alpha. And the state we get here looks thermal and it doesn't follow the page code. We'll talk about that a little more in a second. But another thing you can do is compute with N replicas. And if you compute with N replicas, you now have N copies. So this row N has N sets of indices, I1, J1, I2, J2, IN, JN, which means you're computing this amplitude with N insertions of this boundary operator. And then we have, importantly, one sum over alpha, but N copies of our eigenvalues. So we can sort of, this is throwing away the indices. Another way of writing this is that we get a density matrix. So this is this density matrix for N black holes, for N sets of Hawking radiation, I should say. So maybe we're doing an experiment, we collapse N black holes, and we make sure that when we collapse them, we do it in exactly the same way every time. So we start with the same pure state of ingoing matter. We create these N black holes that are very, very far apart. We keep them well separated from each other. We collect the Hawking radiation from every single one. And then once we've collected the Hawking radiation and we've saved it in our quantum computer, we bring it back together and then maybe do some experiments on it. And the important thing here is that we've got this single sum over alpha, whereas if we were to take the n-fold tensor product of this guy, then we would have n sums over alpha. So these things are not equal. If there really is a sum over alpha, then we don't get the same result. So this is the failure of factorization, and it's the fact that baby universes mediate correlations. So in this case, the baby universes are mediating correlations between different sets of Hawking radiation from entirely separate experiments. Good, we're nearly there. Doing fine. Okay, so corresponding to these two sorts of calculation, we can compute two sorts of entropy. Maybe I haven't paused for questions since introducing the replica wormholes again. So if there are questions now, then.
I just have a quick question. You said that we're computing in number 2, you were computing in N replicas. They're still connected via the boundary, right? When you say it's not N independent systems.
So at this point, I haven't summed over I's and J's and so forth. So that I have.
Oh, I see.
If we're just computing density matrices, then they really are completely independent. But yeah, if you're computing, well, we'll talk about entropies next, and there we're going to sort of correlate them by summing over the indices in a correlated way.
I see.
But still, they are in separate boundaries. There's the boundary of the gravitational region corresponds to n separate, as a disjoint union of n boundaries. Then you sum over the boundary conditions in a correlated way. So that does introduce some connections, and so you don't actually have a factorization problem immediately because you're breaking factorization by this explicit correlated sum.
I see. Thank you.
But nonetheless. Okay, so let's now, corresponding to these two sorts of calculations, let's think about two sorts of entropy you can compute. And these are both perfectly legitimate calculations you can do, and they both calculate something well defined, and they give different answers, but they're different calculations. So the first thing we can do is you compute your entropy by computing the trace of rho Hawking to the n. So this is really just, you compute the von Neumann entropy of Hawking radiation. You do this calculation, this gives you a matrix, and you then take the nth power of that matrix and take the trace. And of course, the thing you'll arrive at is the entropy of the von Neumann entropy that sort of Hawking would have computed, if you like, which is this von Neumann entropy of this state with an average over superselection sectors. So this is really we're doing the strict calculation of the von Neumann entropy of Hawking radiation, and the way we set up the calculation means that there are no replica wormholes. They aren't, the rules of the game mean they don't appear. So doing n separate calculations. Fine. But there's another calculation we can do, which is that we take this correlation function, except we contract indices. So this was J1 equals I2 and J2 equals I3 and so forth, and then we sum over indices. So this is just taking trace of rho. And this, of course, does include replica wormholes. So this, at late times, we expect this calculation, if we're taking seriously what we learned yesterday, this calculation will include replica wormholes. Another way to write this is you take this n copy density matrix. So last time we said we had n replicas, so we were computing the density matrix from n black holes. And we compute an expectation value of a particular operator. And that operator is this cyclic permutation operator. So it's an operator that exchanges our n copies. And this is the thing that glues together the replica manifold in. So this pi is the thing that glues together our replica manifold in the usual way. So a simple example for n equals to 2 is pi is the swap operator. It's the operator that takes two systems and exchanges them. And if you measure the swap operator, if you're really doing an experiment on two black holes, you measure the swap operator by exchanging the Hawking radiation, then you're either going to get the answer 1 or -1. And this is the swap test is an experimental way to determine something like von Neumann entropy. So really it's a second Renyi entropy or it's a purity. So if you take this operator, if you take two uncorrelated density matrices and you have this operator pi up the swap operator, then this expectation value is the trace of rho squared, which is the purity, which is e to the minus the second Renyi entropy. So this is what you might do as an experimentalist if your theorists are having an argument and one theorist says that no, information is lost, and the other theorist says that no, information is returned, and we have unitarity and we have a page curve, and you want to tell the difference and you want to give some experimental light, to shed some experimental light on this argument, then this is sort of the simplest thing you might actually measure to tell the difference. So because it's related to this swap test, actually this is something that people do done on trapped ion systems. So it has real experimental. You can really do this, not for black holes and Hawking radiation, admittedly, at the current state of technology, but you can do it for 3 or 4 trapped ions. Okay, so because it's related to this physical sort of observable that you can compute of a swap operator, we're going to imagine that we can sort of take this and imagine that this is given by trace, that this is giving us trace rho to the n, as we would expect if we had uncorrelated systems, and we'll call it the swap entropy. So the point here is that if your n replicas were uncorrelated, that is to say, if the density matrix of n sets of Hawking radiation was a product of the density matrices of a single set, so they're uncorrelated. Then the trace of the expectation value of this permutation operator would be equal to the trace of the nth power of one of these guys. And in that case, so this guy is computing the swap entropy, I'm calling the swap entropy, and this guy is computing the von Neumann entropy. This would be equal. But if you have correlations, they're different. So if our state is given by this sum over different sectors, roughly the swap entropy, you can think of as, it is not quite true because the swap involves a log and so forth, but because the entropy involves a log, but roughly speaking, you can think of it that instead of taking the entropy of the average state, you're taking roughly the average of the entropy. And these things can be very different. And the first one, the von Neumann entropy, what we called option 1 in these calculations, where we don't have wormholes, this gives us this curve. We have information loss. But the second curve involving replica wormholes, this swap entropy, this thing that's defined by these experiments on n copies of the radiation, this gives us our page curve. I had a simple example on a single qubit, but let's not worry about it. Okay, so I think it's time to conclude. And the last couple of minutes. So let's see how far we've arrived. So the idea to begin with was to look at just trying to take this sort of low energy effective theory of gravity, Einstein gravity, very seriously and see what it predicts. And we've arrived at a new conclusion. And it's very important that part of this result was that there are these super selection sectors for asymptotic observers. Maybe I haven't really said what super selection sectors are. So in general, in quantum mechanics, you get super selection sectors when you have access to a limited algebra of operators. So that means you have a quantum Hilbert space, but the algebra of operators that you can measure is not the entire algebra on the entire Hilbert space, but there's some limitations. So for example, if you're a condensed matter theorist and you're interested in spin chains, you might be interested only in operators that act on a finite number of spins. And then you can have super selection sectors. And so this means that the Hilbert space divides up into these different sectors with classical correlations. So we started with a full theory of quantum gravity that was unique and gives you definite predictions for a given initial state. In particular, there's an initial state of baby universes, including the baby universes. So it gives us a definite prediction. But if we restrict ourselves to asymptotic observables, then we have this classical uncertainty. This classical uncertainty is this sum over alpha p alpha. And the reason why we have a single unique prediction for the complete theory, but this classical uncertainty for asymptotic observers, is because your asymptotic state gets entangled with these baby universes. And if you live only at infinity, you can never directly measure the baby universes. You can indirectly measure them to infer the state of baby universes. Think of that as learning the state of alpha. But you can't measure it directly. But when you do these many measurements, you're learning alpha, you're sort of collapsing the state of the wave function into a particular value of alpha. And in the end, all your observations are going to be compatible with a single row alpha. So it means, for example, that this von Neumann entropy is a legitimate prediction of the theory. It says that there's this entropy that follows the page curve, But an observer, an asymptotic observer, can never see that. In principle, it's completely unobservable, this von Neumann entropy. Instead, you've got this swap entropy that is a proxy for what you would deduce as the entropy by experiment. And this is defined sort of operationally, and that's the entropy of these individual sectors, and that's the physical thing that any observer would really see. So you can never see this actual, the sort of true von Neumann entropy is something that you can calculate with the theory, but using asymptotic observables, you can never see it experimentally. Okay, so Bartek, perhaps you'll indulge me with 2 minutes just to, this is my last page to.
Oh, no, no problem at all. We want to hear your last 2 minutes for sure.
Okay, so this really gives us, this picture is, I think it's not complete in that there are sort of technical checks to make sure that this all hangs together, but it's really a coherent picture for how gravity is working that seems to remove lots of the old puzzles, and the information problem in particular is really a resolution where there's no mystery and there's no it's coherent and self-consistent anyway. But there's a big problem here, which is this. There's that ADS-CFT is a counterexample, if you like. At least in specific examples, things like NX4 super Yang-Mills, this is really bad because at least we think we know exactly what the set of superconformal field theories looks like, and it doesn't seem like there's any room for an ensemble for alpha labels. It just doesn't seem to be possible. So the big question here, and something that I hope that the audience will help us solve in the coming years, is to ask what happens in this case, and how we resolve this tension. So the sort of old information puzzle in my mind has sort of mutated and taken this new form of the factorization puzzle, and this is something that's broader. It gets specifically becomes very sharp in this context of black hole information, but it's something that's more general. So I'll just suggest a few sort of possibilities. One is that there's just something that disallows space-time wormholes. But this is kind of a shame because they give sensible answers for lots of things. So we talked about one example in particular, which was replica wormholes. There are other cases where they also give sensible answers, and in many of those cases, they only give sensible answers if you have an ensemble. They wouldn't give sensible answers for a single unitary theory. So this is certainly possible, but it's sort of a shame. And if this was true, it would seem to me that we haven't learned anything from the replica wormhole story. So I don't like number one. And another two possibilities that may be overlapping is that this was related to a question that was asked earlier, in fact, is that we're only really doing a sort of semi-classical approximation or looking at the low energy theory. And we're using some asymptotic series to talk about the theory. So it could be that there's some way in which the low energy theory or some approximation, it can't give us an approximation to things like the state of Hawking radiation because it's something extremely complicated that depends in great detail on the short distance physics. But it does the next best thing, which it sort of fudges and gives us an average over what it doesn't know about the high energy theory. So that's one possibility. And then the way to explore this is to try to understand how the ingredients of string theory, for example, would come in to solve the factorization problem. And the last part, which I think is I think both of these are true together, is rather than disallowing space-time wormholes to solve the factorization problem, you should solve it by adding extra things in. And so one example that I think is really nice that Steve Schenker talks about is that if you have some over some random phases, e to the phi I minus phi j. This factorizes. If you average over these phases, then you can, if these phases are very incoherent, all the off-diagonal terms tend to cancel. And you arrive at something like just a sum over I, so that the diagonal piece, I is equal to j. Maybe there's some coefficients here, c I j, and you're left with c I I. So this seems like a good approximation, and this piece you can maybe think of as being a little bit like a wormhole that connects the two pieces. But the way we get to this that factorizes, this should be, I guess this should be ci times cj. The way you get to this thing that does factorize is not by throwing away the diagonal pieces, it's by adding back in the off diagonal. And there's a lot more that could be said, but it seems that gravity is not doing this stupid thing of throwing away space-time wormholes entirely. It's keeping them because they're doing something nice, but it's solving the factorization problem in a cleverer way that we can work to understand over the next few years. So with that, I'll thank you for your attention and